week we'll go over rotations. We'll also go over something called congruent. So rotations, pretty intuitive. We're just tacking on one more type of transformation. So remember, in our transformations, we had our translations. That was kind of like our shift. So we'll just call that a shift or a slide of a figure. We had our reflections. We'll call those our flips. And we're going to tack on one more, kind of the most intuitive of all. I think it's just the rotations. We'll call those our spins. And so essentially what we're going to do is we're going to try to do, I'll just go over the learning goals, but we're going to try to understand how to rotate in a coordinate plane. And then we're going to try to understand what a congruent figure is. And then we're going to try to figure out how rotations, reflections, and translations all kind of show congruency. So I'm going to kind of give you the definition of congruency right off the bat, because it's not all that complicated. It's basically just saying that we got two figures. If they are the exact size and shape, then they're congruent. So you could rotate something, you could reflect something, you could translate something, you'd shift a shape around, it's still the same basic shape. And when it has those properties, same size and shape, we call those congruent. So there's a little bit more geometric definitions that you'll get to kind of when you get to geometry, which is Math 10. However, this is kind of our basics for Math 8. So we're going to start our jumping off point for this lesson is going to be that exploration problem I gave you on Friday. So if you haven't done that, it's not a problem that takes a long time, probably about like 3 to 5 minutes, but go ahead and pause this video, do that first. That'll kind of be our jump off point into this lesson. So let's start. We've got our exploration problem. So we had Maria, she was on board in the bottom of the Ferris wheel. That's where Maria was at the start. And she rides to the top where the car stops. So Maria tells her friend she completed a 1/4 turn. So I think a lot of you will say, I don't agree with Maria at all, because 1/4 turn, if you would take this, split it up into quarters, that's 1/4 right here. If we were to undergo this to get to our ending point, that obviously be a half. So no, we'll write a half turn. So there's another way we can analyze this. So we can also analyze this in terms of degree. So I'm going to bring my protractor tool onto the page really quick, and we'll just kind of rotate it to where we can get the starting point. So remember, reading a protractor, we'll just count the initial point. So it starts here at 0 degrees, and we rotate up till we get to here. And notice I've kind of placed the origin right at the center of the Ferris wheel here. And you can see that, well, that's a entire 180 or a half turn. So we could just say that's a 180 degree rotation. And that's what we're going to kind of study today. So pretty quick jump off point. Let's jump into some actual math on this. So we're going to start, we'll start by clearing my protractor tool, but we're going to start by just analyzing a rotation without any kind of formal math going on at all. So we've got this triangle MLJ, and don't be confused by this. This is just saying it's got the point M, the point L, and the point A, or J, so we call that triangle MLJ. And we're going to try to explain with the language of rotation that it became the triangle M prime right here, this point, L prime, this point, J prime. So how did this triangle here, this black triangle, become this blue triangle? And so what I'm going to do to illustrate this is I'm just going to rotate the entire coordinate. So I have two images kind of under each other. So what I'm going to do is I'm just going to take this right here, and I'm going to rotate it right across the center. So right across the origin, I'm just going to rotate it. So I'll go a 1/4 turn, or 90 degrees, and we'll put some terminology on that as well. Let me get that exact. It's not quite. There we go. So as you can see, I rotated 90 degrees that way. We'll call that a 90 degrees counterclockwise, so the opposite of the way a clock turns. And as you can see, if I look at this and I cross out, so I've got a new coordinate system now, I've rotated MLJ over. So let's call this now M prime, L prime, J prime. And let's verify that that's the same as this shape right here. So let's ignore this because this is now nothing. But if I look at this now, this is now the X and this is now the Y. And so we can look at this. So J prime is left 3 or negative, or excuse me, left 2 or negative 2 on the X, 3Y. Looks like that's the same here. So negative 2 comma 3. Same coordinate here. Looks like the same for L prime. I am left 4 up 4 or negative 4 comma 4. That is the same here. So we've checked off 2 of them. And M prime looks like I'm left 5 up 2 or negative 5 comma 2. We have checked off every single piece. So every single vertex here, the L vertex, the J vertex, the M vertex, they're all in the same location. So you can see it just underwent a 90-degree rotation. So we're going to look, we're not going to dive super deep into this to all of it because they'll kind of do that in geometry, but I'm going to do the basics of how to kind of implement this by hand, or what you would do. So this one, just to make it kind of obvious, I've got the rotation already, but we're basically going to rotate, we'll say that triangle UIQ, and we're going to rotate it 90 degrees, and I should specify because I'm rotating it this way. So let's specify that we're going clockwise. So what I'm going to do is just kind of implement that rotation a little more formally to show you how you would do this. So we want to be careful here because this one's actually probably the trickiest of the 3 types of transformations, but we're going to rotate this triangle here 90 degrees clockwise. So what I'm going to do is I'm essentially just going to draw a line from the origin to each point in the figure, and then I'm going to rotate that line 90 degrees. And you can kind of intuit, well, if this were a 180-degree rotation, I would just swap this step out for 180 degrees. If it was a 270-degree rotation, I would do the same here. And so let's go ahead and start by drawing a line. We'll start with point I to try to rotate it to I prime here. So what I'm going to do is I'm just going to draw a line, and let's kind of keep it color coded. So we'll take point I, and you can see that I've gone to the left 5 and up 2. So now if I were to rotate this 90 degrees, I want this to keep the same size. And we'll kind of do it, and then we'll re-look at it once we're done. But essentially, if I were to take this line and rotate it, I'm now going from left 5 to up 5, and from up 2 to right 2. So I have kept this line the exact same magnitude or same length. So both the black line and the blue line have the same exact length, and they're exactly at a right or 90-degree angle. And I could just do that with each of the points. So I could draw a line from, let me make sure this is color coded. I could draw a line from Q, and if I kept that the same magnitude or length and rotated it to Q prime, I would just draw a line here. We've got our 90 degrees, so negative 2, 2 became 2, positive 2. And then we'll do one more. Let's rotate U to U prime. So draw U up here, and actually let's get that in the same color set. Draw U here. We'll draw it through our Q line, and we want to keep the exact same magnitude. We just draw it 90 degrees over to U prime. So what was left 4 up 4 becomes right 4 up 4. So all you have to do is draw the lines, rotate them. And so that's kind of how you implement a rotation. So let's circle back to the beginning really quick. So we've got our translations down and reflections from last week, and now we know how to do our rotations, at least informally and a little bit formally with the math. So we're going to see now how we can use all three of these to kind of prove a shape is congruent or not. So remember, the figure has to have the same size and the same shape. So there can't be any discrepancies in that. And so we also know if we just rotate, reflect, or translate, so if we shift, slide, flip, or spin, we don't change the size or shape. So if we can look at basically two figures and show that figure 1 can rotate, reflect, or translate to figure 2, we verify that it's congruent. So we're going to look at that real quick. So we're going to do two examples on this. One, actually, I will say one that does satisfy, one that doesn't, and we'll kind of see how we prove this. So we're going to start with the quadrilateral ABCD. Again, they're just saying the vertices, so it's got point A, B, C, and D, and they're connected in that order. So A connects to B, B connects to C, C connects to D, and that's how that terminology works. And so we're going to see if it's congruent. So again, let's just rewrite this in a little bit more friendly language. We're going to verify that it has the same size and shape as this quadrilateral in the first quadrant. So let's go ahead and take ABCD and let's strategize here. So we want to go through, we've got kind of three things in our tool belt to work with. We could rotate, we could reflect, and we could translate. So we definitely probably got to translate, but first, if you look at this, this looks kind of like a mirror image here. So I'm going to do kind of the easiest reflection of all, which is just reflecting across an axis. And you can see I could reflect it down, but that doesn't look like it has the same shape. It looks like QT and AD, these two lines, are pretty similar, but however, I just got to flip it this way. So my step 1, before I clear, I'm just going to choose to reflect, and I want to be very specific here, across the y-axis. So I will go ahead and do that. So let's do a different color. So I've got the first shape in black, the last shape in blue. Let's make the middle shape kind of the reflection. Let's make that, we'll just color code it. All of that will be in red. So we'll do our shape, our reflection across the y-axis, and I'll just kind of underline it in red to really drive that point home that this first transformation is going to be in red. So we'll just go ahead and reflect everything across this y-axis right here. So C is 1 left of the y-axis and 3 up. So let's just make it 1 to the right and 3 up. So again, same distance across. We'll say that's C prime. We'll do the same thing as D. It's 3 away from the y-axis. So let's just draw it in the same y-coordinate, but 3 to the right of the y-axis. This will be D prime. Do the same thing with B. It's 5 away. So let's draw it 5 away over here. And that'll be B prime. And then finally we got A, which is 4 away from the y-axis. Let's draw it 4 away from the y-axis on the other side. And we've got A prime. And then we can just connect our lines. So I'll go ahead and do that now. So we got C connects to D, and let me redo that in red really quick so it all stays consistent. We got C connects to D. We'll also do A connects to D there. We'll do B connects to C. And let's also do A connects to B. And we can kind of see now we're pretty close. So I could rotate. That doesn't seem to do much good. Reflection, I've already done my reflection, so that kind of seems like a little bit of a redundant task. So now we can just kind of see, well, if I were to take every point and just push it down 2 and to the right 1, I would get that exact shape right there. And so step 2, if I wanted to basically transform ABCD into quadrilateral QRST, I can just do these 2 steps. 1, reflect across the y-axis. 2, let's translate down to right one. And just to reflect back on that terminology, you could always say that this is like the coordinates x, y translate to x, we're going to the right one, so +1, and we're going down 2, so let's take the y coordinate, subtract 2. And so because we're able to take these two steps and basically transform it exactly overlapping to this shape here, we could say ABCD is congruent to quadrilateral QRST. So we say yes. And we could even use some formal math language here. ABCD, we'll write our congruent is congruent to QRST. Same exact shape. So now let's look at another one. Let's look at B, and this one we're not going to put a little formal math because we can actually use our skills of just kind of analyzing a reflection to prove it yes or no. So what I'm going to do here is we're going to first formally introduce, well, what is this symbol here? That's kind of new. So this is just triangle. You see the triangle symbol ABC. So triangle ABC. We've got it there. Just as A connects to B connects to C, then it loops back on itself. Is it congruent? So that's what this symbol means, to triangle JKL. So we're going to analyze this, and I've actually separated off. You'll notice that I can actually just take this, move it around, move it off of it. But we're going to take it and we're going to rotate it 90 degrees that way, or 90 degrees counterclockwise. So I'm going to take this shape and we're just going to rotate it 90 degrees. So I'm going to do this a little roughly because we don't actually need super precise math. So I'm going to rotate it 90 degrees clockwise, which puts us about right there if we were to do it. And you could see now I just need to translate. I need to shift. So I need to shift it that way. And if we were to shift it that way, you can just see by looking at both of them together, if we were to try to overlap it, A and B would occupy the exact same coordinate as J and K. However, we cannot make it so C maps onto L. This leg here from A to C and this leg here from B to C are longer than these two legs. So there is actually no way to translate or transform this shape to create this shape. So we say on this one, not congruent. So hopefully that all makes sense. So I hope to see you all on Wednesday for the office hour. So if any of this didn't make sense, write those questions down, bring them to the office hours. So we'll kind of have a review session on that, and then we'll dive further into the topic next week. But I will see you guys on Wednesday. Take care.